The next contestant is Kensen Shi from Texas A&M Consolidated High School in College Station, Texas.
Hello, my name is Kensen Shi, and my project is Lazy Toggle PRM, a single query approach to motion planning. In the motion planning problem, we are first given an environment, which includes descriptions of a movable object, which is usually a robot, and a set of obstacles. We're also given a query, which includes the start and goal configurations, and we wish to find a valid path from the start to goal, where valid usually means collision-free. Motion planning has many applications. For instance, it can benefit robots associated with assembly lines, search and rescue missions, robotic medical surgery, and much more. In animation and video game design, motion planning can help create realistic motions for autonomous virtual characters, and in structural biology, we can model large molecules as robots, and thus motion planning can simulate protein folding and ligand binding. The complete motion planning problem is computationally hard, so we use randomized approaches to calculate approximations. Before we dive too deeply into motion planning, it is important to understand the concept of configuration space, or C-space. It is an abstraction that allows for the similar expression of any robot type. Any robot configuration can be fully described by n parameters, one for each dimension of movement. The set of all possible configurations thus forms an n-dimensional space called configuration space. For example, an airplane has 3 spatial coordinates and 3 rotations, the pitch, yaw, and roll, so its configuration space is 6-dimensional. C-space is divided into the free space and the obstacle space, which are the subsets of valid and invalid configurations, respectively. The probabilistic roadmap method, or PRM, is one of the most widely used methods to solve the motion planning problem. It constructs a roadmap, which is a graph within the free space where the vertices and edges represent valid configurations. An example environment is shown on the right. PRM begins with the roadmap construction phase, which randomly generates configurations that become vertices in the roadmap. Invalid configurations are discarded. Then, nearby vertices are connected to form edges, and again, invalid ones are discarded. These edges are computed using a simple local planner, which in most cases is simply straight line interpolation through C-space. Then, in the query phase, the start and goal are connected to the roadmap, and a graph search is used to find a valid path. There are 2 main weaknesses of PRMs. First, they require many validity tests to validate the roadmap, and second, they are inefficient at mapping narrow passages. 2 PRM variants separately tackle these gaps. First, lazy PRM reduces the number of validity tests needed by delaying validity checking for as long as possible, namely until a path is extracted. In this way, lazy PRM only validates parts of the roadmap relevant to the query and is also best suited for single query scenarios. Lazy PRM also has the option to request different levels of laziness. For example, we could validate all the vertices before adding them to the roadmap, and thus using only lazy edge evaluation. Toggle PRM is another PRM variation that improves the mapping of narrow passages by constructing roadmaps of both the free space and the obstacle space. It uses witnesses, which are configurations along an invalid edge that are guaranteed to lie in the opposite space. For example, if we have 2 vertices in the obstacle roadmap that are on opposite sides of a narrow passage, their edge connection will fail and will lead to the discovery of a valid witness within the narrow passage as desired. Toggle PRM is provably better than uniform random sampling in certain narrow passages and experimentally better than other sampling techniques. In my project, I introduce Lazy Toggle PRM, which unifies the benefits of both Lazy PRM and Toggle PRM to simultaneously address both main weaknesses of PRMs. I also experimentally analyze its effectiveness, demonstrating improved efficiency. Lazy Toggle PRM begins with a lazily constructed roadmap. It then iteratively extracts and validates paths and uses the invalid portions to feed a Toggle PRM strategy. After an initialization phase, Lazy Toggle PRM loops over the lazy roadmap construction, path validation, and witness processing phases. This is the Lazy Toggle PRM algorithm with the 4 phases shown. We will now examine each phase separately. During the initialization phase, we have a free roadmap, an obstacle roadmap, and a queue, all initialized to be empty. The queue will be later used to store witnesses. Then we add the start and goal configurations to the free roadmap, and until we find a valid path, we repeat the other 3 phases. In the lazy roadmap construction phase, we lazily generate and connect vertices in the free roadmap until the start and goal are in the same connected component, which implies that a potential path exists. Then, in the path validation phase, we extract such paths and validate them. We validate the vertices before the edges, and any invalid portions are deleted from the free roadmap, and their witnesses are saved in the queue. If all the vertices and edges are valid, then we conclude that the entire path is valid, so we return that path. The path validation phase ends when there are no more paths left. Then, in the witness processing phase, we handle the witnesses stored in the queue. The invalid witnesses are added to the obstacle roadmap and connected in a non-lazy manner, which can yield valid witnesses that are again added to the queue. Valid witnesses in the queue are added to the free roadmap and connected lazily. The witness processing phase ends when either the queue is empty and all witnesses have been processed, or the start and goal are connected by a path. After the witness processing phase, the algorithm always returns to the lazy roadmap construction phase. However, if a path does exist, the lazy roadmap construction phase will proceed directly to the path validation phase. As an example, we will follow this algorithm in this simple environment. The free space is shown in white and the obstacle space is shown in black. During initialization, the start and goal are added to the free roadmap. These are denoted by an S and G respectively. Then, a lazy roadmap is constructed. Note that in this example, the color gray is used to show parts of the free roadmap that have not yet been validated, and blue is used to show parts that have already been validated. Then, in the path validation phase, we extract paths and validate them. It turns out that each of these paths are invalid, so we delete the invalid portions and save their witnesses, which are shown in red. These witnesses are added to the queue. Then, in the witness processing phase, we add these witnesses to the obstacle roadmap and connect them in a non-lazy manner. One of these connections has failed and has yielded a valid witness within the narrow passage, which is then added to the free roadmap and connected lazily. Again, in the path validation phase, we find that an edge is invalid, so we delete it and save its witness. We process this witness and obtain another valid witness within the narrow passage. We repeat, saving 2 more witnesses, and obtain yet another valid witness within the narrow passage. And finally, we extract a path and validate it, only to find that it is completely valid, so we are done. I experimentally analyzed my algorithm in the following 7 environments. The top row shows 5 basic environments, and the bottom row shows 2 complex and realistic environments. In the helicopter environment, the robot is a helicopter that must traverse through a cityscape with buildings and wires. And in the building environment, a large rectangular robot must pass through very narrow doorways in a building floor plan. I tested lazy toggle PRM, lazy PRM, toggle PRM, and the traditional or basic PRM. I also tested different levels of laziness, which accounts for the sub-methods within lazy toggle PRM and lazy PRM. Also, validity tests were always done as collision detection tests, or CD tests. In other words, valid is equivalent to collision-free in my experiments. Here we have the collision detection test used in the basic environments. Note that this graph uses a logarithmic scale. As was shown in previous work, lazy PRM reduced the number of CD calls compared to basic, and I show that lazy toggle PRM replicates this benefit. Lazy toggle PRM is shown by the 3 leftmost bars in each section, and we can see that it reduces the CD calls by a factor of about 10 compared to toggle PRM. In the complex environments, we see similar data. In general, lazy toggle PRM uses the fewest CD tests out of all the methods tested, and especially in the complex environments, these CD tests comprise most of the solving time. Here we have the overall efficiency in the basic environments measured in the time required to solve the query. In the very simple environments, CD tests are quite cheap, and thus graph searches cause inefficiencies in the lazy methods. An increased number of graph searches is an inherent part of lazy evaluation, since paths must be repeatedly extracted. However, even in the environments not particularly suited for lazy evaluation, namely those very simple environments, lazy toggle PRM is still among the best of these methods tested. In the complex environments, time differences are much more pronounced, and lazy toggle PRM shows its true power. In fact, it outperformed all other methods tested, solving queries 2 to 4 times as fast as the next best method in each environment. In conclusion, I introduced lazy toggle PRM, which is a novel unification of lazy PRM and toggle PRM that simultaneously addresses both main weaknesses of PRMs. I also demonstrate its effectiveness in many scenarios, showing a speedup of 2 to 4 times in the complex environments. In the future, we can improve lazy toggle PRM by tracking the relative sizes of the two roadmaps to dynamically reach an optimum level of laziness in the different environments. We can also apply this algorithm to other situations in motion planning, such as in dynamic environments, articulated linkages, and multi-robot systems. Finally, we can study the use of lazy toggle PRM in the many applications of motion planning. Remember that virtually all robots have to move around without colliding with surrounding objects and can thus benefit from the study of motion planning and therefore also my new development, lazy toggle PRM. These are my references. And finally, I would like to thank Dr. Nancy Amato for being my faculty mentor, Jory Denny for being my graduate student mentor, and all other members of the Parasol Laboratory at Texas A&M University for their support. I would also like to thank the Siemens Foundation, the College Board, and the George Washington University for providing me with this wonderful opportunity to share my research. Thank you for your attention.